Good morning, good afternoon, good evening, wherever you are. Welcome to this presentation of server predictive multiplayer gaming, mitigation of data loss effect. This is a technical report that Mpai has just published, and this is an opportunity for you to get inside the very interesting world of multiplayer gaming. But before that, let me give me 2 words about MPAI. MPAI is moving picture, audio, and data coding by artificial intelligence, an international, unaffiliated, non-profit association based in Geneva. So, of course, we develop standards, and here's what you see. The mission is to promote the efficient use of data in several ways. First is developing specification for the coding of any type of data using especially artificial intelligence, but also technology that allow us to integrate AI technologies into ICT, information and communication technology system. So this is the technical side, but we also want to contribute in making the specification available by adding to our technical specification IPR guidelines that helps the people who wanted to use the standard. We operate based on the open international collaboration of interested parties that support the Mpai mission and the means to accomplish it. The mission is what I've said before, and the means to accomplish it is the bridging the gap part. So let's first say a characteristic of Mpai standards that we want them to be explainable. So for instance, let's take a case that we have a person speaking. We have a module, we call AI module, that analyzes the speech and provides the text that is being uttered in the speech and the identity of the speaker. So in a more complex situation, you have several of these AI modules, and here is what you see, and they are interconnected so that they can be considered as a workflow where you have input data coming in, there is an AI module processing, there are processed data passed to another AIM, and so on, until you get the result that you are seeking. So this is the basis of one of the first standards that we have developed, which is called AI framework. But let me go to the other part of the Mpai work, which is to make a standard accessible and timely available. And how do we do that? Before we started developing our standard, we develop and adopt a framework license. A framework license has a main characteristic that it is not a license because it does not have values, it does not have dollars, percentage, dates, and so on. But the framework license declares that the eventual license will be issued not after products are on the market. So the implementer are on an equal footing at a price comparable with similar standard technologies. During the development, any member making a contribution declares it will make its license available according to the framework license. After the development, members holding IP in the standard selected the preferred patent pool administrator. So, and here's where the Mpai role stops. Of course, we facilitate, but then we stay aside because the actual exploitation of the standard is not our business. Another important feature of Mpai is that we have a very rigorous standard development process. So we have an idea, we start collecting the interest in this idea, we develop use cases, and we develop functional requirements. The interesting point is that anybody is allowed to participate in these three phases. Because the spirit is that we are working for making our standard useful, and therefore the requirements should come from as many sources as possible. But then, Mpai members, and in particular principal members, develop the commercial requirement, which is by this we mean the framework license. We develop a call for technology, and then we develop the standard. When the standard is close to publication, we publish it not in a final form, but for community comments. We receive comments, we try to add, to accommodate the comment that we have received to the specification, which is eventually published, and then we also publish the reference software, conformance testing, and performance assessment. I mean, at least this is in the process. What have we done so far? So we have some 14 standards, and we have one technical specification, this red one that you're seeing here, but we have a standard that applies to many other areas. We have the AI framework that I've talked about. We have something on audio, connected autonomous vehicles, finance, human and machine communication, multimodal conversation, the metaverse, watermarking, object and single screens, portable avatars, profiles, and data type performance and attributes. I mean, they are all a part of a general idea of Mpai standard. We are working on new standards. In some cases, they are continuation of what we had, in the sense that we had more features and more technologies. In some cases, these are the black ones, are entirely new standards that are being prepared for health, two standards for video coding, and one standard so-called for XR venues, in particular live theatrical performance. With that, I look forward to working with you in Mpai project. As we see, we have many of them. So yeah, I encourage you to join Mpai, share the future, share the fun, and build the future. And here you have a link to the webpage where you can see more about Mpai. And now let me give the floor to Francesco, who has been the chair in this activity for the past few years. But let me take the opportunity to welcome also Marco, who was the one who really kicked off this activity, and he had I mean, it's really to be commended for a forward-looking idea. Francesco?
Hello everyone. Yes, I also thank Leonardo and Marco for the opportunity of tutoring this group, the Mpai SPG group, and more formal greetings will be also at the end of the presentation. Yeah, so I'm here and I would like to make an overview of the work we've done with SPG, the context in which SPG operates, and what was the output of this years of working together. So as the name suggests, introduced by Leonardo, the SPG stands for Server-Based Predictive Multiplayer Gaming. Mitigation of data loss. So the context in which we are proposing this technical document is that of, okay, if I can go forward, okay, is that of online multiplayer gaming. Of course, this is a really rich and expanding industry. Many popular games are played online by multiple users. And of course, this is really a training factor within the gaming industry. How are online multiplayer games built, and what is their underlying structure? There are different types of architectures. However, two are among them are the most popular. We have, in fact, authoritative servers and the peer-to-peer networks. I'm just making this little introduction just to give some context on the decisions and that we made throughout the MPI SPG process. So in the authoritative server, the idea is that I hope you see. I should still see my my cursor. The idea is that you have a centralized controller, which is the server, and a list of n clients which connect to the server, which holds a shared instance of the game state and distributes this information to all clients based on the updates he receives from each instance. The same architecture can also be actually applied, making one of the players, one of the clients, an actual server, but the idea remains the same, that we have this centralized control. Of course, this ensures a better consistency. It's more secure in terms of data corruption and so forth. So it is, for this reason, it is one of the most widespread network architectures out in the used within the gaming industry. Just for completion, another structure, it is that of peer-to-peer, but I wanted to stress this context because we will be working in this in the addressing the problem related to authoritative server architectures. So online multiplayer gaming, of course, unfortunately, faces some problems due mostly, of course, due to the network, to the fact that the game it's a shared instance of multiple other instances, and these problems usually arise from having a corrupted version of the game state, which can be derived from several factors. For instance, having losing data over the network, having data which is delayed due to latency, and thus the synchronization between all clients becomes impossible. And finally, of course, even the data corruption. So a malicious user could, in fact, decide to inject fake data within the network, thus compromising the shared state of the game. Of course, some of these problems have been widely tackled throughout the years because, again, the wide popularity of network gaming. Among the most popular the techniques which help to either mitigate or compensate these issues, we can see time delay and time warping, which are uh, two techniques which act on the server. So I want to make this little distinction between these mitigation techniques can be either be executed and controlled by the server, or another example, it's that of, for example, client prediction, where the prediction, in case of one of the problems I mentioned earlier, it's handled by the client and then reconciled with the server. So in this context of issues, problems, and and solutions, falls the idea behind the MPAI, which yields some several key words and factors. In fact, the idea is that we want to create a solution which is server side. So the idea is that the compensation techniques acts and behaves on the server. uh, Prediction. So the idea is to leverage a prediction to compensate for the absence of data using a prediction, but compared to other solutions more widely adopted, the idea, of course, falling under the MPI community is that to leverage the AI technology in general. So exploit the potentialities of artificial intelligence to create more accurate predictions. And now, the idea behind so the specificality of this technical report is that to tackle the problem of data loss, which can be either due to missing data or delayed data. Yeah, so we can go further. So I will now give you an overview of which is the reference model upon which SPG was conceptualized and then implemented. So here it's a little diagram. So on the right side, we have what is the online game server. So the instance of the game server, which on the further right communicates with a number n, so a variable number of clients. How is the process works? Each client sends some client data to the online game server, which processes the data, sending back a new updated game state, this GS, to each client, so that the GS state sent to each client it's equal for everyone. ensuring thus consistency of the game. Attached to the online game server, so SPG is envisioned as a module which communicates with the server without overriding its functionalities. The idea is to send continuously the previous state of the game. So the GS state at the instance previous at the current instance is sent to the SPG module. The SPG module then the general idea is that it computes a prediction, so creates a predicted version of the game state, which is sent to the online game server, and thanks to the predicted version, the game server can decide either to use the computed game state computed thanks to all the client data received from the client, or if it is necessary, substituted with the predicted version. So what happens within the game state, within the game server, each client sends the client data. As I said, we have a game state engine which processes the data in order to create the game state data, which contains all the information to reconstruct the game. Within the line game server, we modeled we generalized the behavior of an authoritative server, defining three core engines, each in charge of a specificality of a game. So the physics behavior, the physics, the behavior engine, and the rules engine, which compute a series of game messages based on what is received by the game state engine, based on the data received by the clients. And all these messages are composed by the game state engine, creating, as I said, the game state. At the same time, the game state is sent, as I was saying, to the game state, to the SPG module. And the SPG module simply does process the game state through the game state multiplexer, demultiplexer, recreates the behavior, so simulates the behavior that we see on the game server, but instead of computing based on data received by clients, computes a predicted version of the specular messages based on the past messages received. Thanks, all these messages are then composed together, creating a predicted version of the game state, which as I said earlier, then is sent back to the online game server, which then distributes the information to everyone. So based on this general conceptualization of the problem of predicting the game state through SPG, what we decided was how can we make this how can we generalize this concept and making it applicable to games. So first matter that we encountered was realizing that the games are intrinsically very different from one another. So each game has its own mechanics, its own entities playing the game, different rules, different behaviors. Thus, completely generalizing in order to create a full standard of this SPG process, we realized was almost impossible. So finding a standard that fits all of the possible variations a game can have was difficult. Therefore, instead of defining a standard, our first goal was that to define a process. The idea was this: that through this process, we would provide a series of guidelines which would be documented in a technical report, and practitioners, people interested in trying to experiment with this approach to mitigation and to the mitigation of data loss, can then consult the technical report and try to reapply to their specific game what we did. Therefore, we created a document where we redefined 10 steps. These 10 steps, as I said, are composed of a high-level guideline which tells you what you should do. And we also provide for each of these steps an implementation example, which tells you how we did implement the guideline that we describe. We did this implementation using a car racing game that we implemented from scratch again, as a reference example. So let's now, so these are a brief overview of all the 10 steps. So, but let's not delve too much onto this slide, and let's go and see each one of them in sequence. So, of course, the first part, the first thing to do is select the game that you wish to integrate SPG in. So the idea behind the guideline that we provide in this case is that the idea is that SPG theoretically could be applied to any multiplayer online game. Of course, it must be constructed and built using an authoritative server architecture, because this was the founding, yeah, was one of the foundations upon which we started the SPG. And the other important part is that SPG must be embedded in the game. It means that SPG must strictly communicate with the informations and processes of instances of the game itself. Therefore, it is important that to integrate SPG, it is necessary to have access to the source code. In fact, this integration is not yet available and possible. Imagining SPG as a completely separate instance that just communicates with the server, it must be integrated within it. So, as I said, in order to meet this requirement, our decision was to start a game from scratch. So we developed a game from the ground up. This game, as I said, it's a car racing game, and in the second step of the process, once you have decided the game that you want to play as PG, is to identify the entities which affect the game state in order to understand and decide what should be predicted, which are the information necessary to predict the game state in order to then distribute this predicted version. In our example, so what we understood is that we have the entities that make the game, that are part of the game, are these cars that you see in this colored um, purple and red, which as a racing game race along a custom track. Once we have defined the entities, as I said, we must, the important part is define which is the minimal set of information and entities of properties associated with these entities which affect the game state. Because we do this, because we need to find the perfect balance between having a good prediction accuracy, thus having a substantial amount of data to use for the prediction, at the same time balancing it with the model complexity, because a key factor which must be understood is that these processes, this prediction game states which are computed by the SPG module must be executed in real time. So as games should theoretically aim at a 60 hertz refresh rate. This means that each prediction must occur within 16 milliseconds. So the time is really short, and therefore having a model which is lightweight and suitable for real-time computation is important. Therefore, this balance between prediction accuracy and model complexity is a founding factor when understanding which are the minimal set of entities necessary to create the game state. In our case, how do we recreate completely a game state? We understood that is simply the only necessary information is the spatial attitude of cars. For us, spatial attitudes is a composed data structure which contains the position, the orientation, velocity, and acceleration of each car. Of course, composing all this information for each car at every time step, we're able to recreate the state on the game server. In fact, as if we see here, as the car drive along the track, once we have the single information, so the spatial attitude of each of these car, on every client, we're capable of recreating the same shared instance. So what do we need to predict? In the end, it's the special attitude of each car, which then compose creates us a predicted version of the game state. So of course, as we are in the field of machine learning and training and using neural network models, the training, having a data set necessary for training, it's crucial and fundamental. At this point in the guideline, what we underline, it's that users have two options. Of course, the first and most easiest route is that to find the data publicly available. So what it means that for a particular game, there already exists a rich enough data set containing all information of the game. So all those data which make and compose the game state, which can be used again for training a model. On the other hand, if data is not available publicly, it is necessary to create a data set because we need it for training the models. At this step, again, there are two other options. In fact, we have the possibility of creating a data set based on human player data, which means that we play several multiple instances of the game, collect data from from human players. Of course, this is a less convenient approach. In fact, it requires it's a time-consuming process as you need to gather people, make them play, collect the data, and so forth. At the same time, of course, it yields us better and more accurate results since we are trying to simulate and predict player data, human player data, put training network models with the same data. It's more efficient, it's more accurate, yields better, can yield better results. On the other hand, of course, there is another approach, which is that of leveraging AI player data. AI agent players, which means that instead of making the game sessions played by real players, we make them play by AI agent players, which mimic as effective as possible real human players, and we collect data in that case. Of course, this approach is a lot more convenient because it's just a matter of computational resources and time to make the game run and collect the data. Of course, having created a synthetic data set can have some domain shifting issues when shifted to trying to predict real players. However, it is a good starting point. In fact, what we did for our example game, for the car racing game, was to exploit autonomous AI agent players, which played numerous sessions of the game where we sampled data every 20 milliseconds, creating a dataset composed of 2 million records. The records were then divided into three different sets: the training, the test, and the validation set, which we used during training. Each record of this data set contains, of course, the car's special attitude, so the data associated with the entity, with the car entity, and at the same time, informations about the surroundings, so environmental data associated with the car. So where is the car within the world, which are its surroundings, and so forth. So we collect. So the data is composed of these two layers of information. The sixth step. So here I put together the fourth and the fifth, which are more detailed in the document, but I thought it was as convenient to do it all together in one. Now, so we jump to the step number 6, where, of course, now we have the data set, we have defined what we expect to predict, and we need to create these models. So as a guideline, the first important thing is to select which is the best, most suitable neural network for the task at hand. In this case, we're speaking, we can simplify it as a time series prediction problem. And therefore, looking at the literature and more modern at the literature and research and so forth, the best neural network model should be selected. Once the model has been selected, the approach has been selected, we should train several models. So we should not stop to just one models, as we need to define a subset of, so we need to test the different training approaches, exploiting, of course, different input vectors. So how do we compose the data on the input side? And of course, playing with the hyperparameters of the network. Once we have done many experiments, playing around with these two variables, the objective is to define a subset of the best performing networks. When I mean performing, I mean the networks which yield the best results in terms of mean absolute error in the validation set. So in fact, what we did during this training prediction step, we decided to leverage a deep LSTM network as a neural network. Our input vector in the end was composed of a sequence in time of the different cars' special attitude together with several information about the environment. What is the output of our of the network? It's each car's special attitude. As I said earlier, thanks to having by having just the special attitude of each car, we are capable of recreating and thus predicting the overall game state. From all our experiments, which I have to say lasted several months, we outlined the four best model which yielded the best results. So these are four models that we selected among the many. I think we trained more than 100 models with different parameters. Now it is not the venue to delve too much into the meaning of the different parameters, but please refer to the technical report to have further details. But the idea here just to show that among a big set of trained networks, we defined and we chose a subset of them. Of course, now that we have a trained model, we need to implement and evaluate its behavior within SPG, so within the game itself. So the prediction module should be implemented, and the neural and the network should be prepared to compute and function in real time. And two issues should be taken into account. One of this is prediction accuracy, therefore, which can be slightly different. So prediction accuracy in our context was measured as the mean absolute error. This metric should be can be of course different between what has been obtained during training and what is then obtained during gaming as the context change. So this is a problem which must be accounted for. And another problem is that of error accumulation, as we will need to predict for a sequence of instances, because data, we could lose data not just for an instance, but for a sequence of instances, accumulating errors due to predicting with predicted data. But let's overview this problem more in detail. So if we have an output which is a game state, which is the result of a sequence of past game states, real game states, so computed thanks to actual client data, when we start predicting, because we lose data from a specific client, we start filling up the input vector with all the with the past game state with predicted versions. What happens is that as we go further, accumulating, if just one of this predicted version had a small error, as we add predicted states to the game, the problem could be that of increasing this the error as we predict in the output using more predicted versions. So what we did was we implemented the SPG more specifically, we did it in the AI behavior engine. So our network model is stored, let's say, into this box, because what we just need to predict the behavior of the car, and we didn't have any rules or physics to process. So just implementing SPG within, so the network model within this uh, box here, we are capable of, as I said, of creating a general game state, a predicted version of the game state. We then computed the mean absolute error for all four models that I discussed earlier. Sorry. Um, and also we assessed the degree of error accumulation. All this was done, of course, within the game. This is an important thing because one is the context of training that we perform it within our Python environment. The other is that to use it actually in the game in real time. So what do I mean by error accumulation? As you can see here, you're seeing a car, which is the car driven by the AI agent. In the yellow version, it's the predicted version. So what happens is that for the first instances, the prediction is accurate and and sticks with the AI driver. However, as the time passes, this error accumulates a little bit, diverging a little bit from the actual instance. So this is a problem which should be measured and accounted for. Here, I want to show you, so how do we assess these two problems? We assess them by measuring the mean absolute error between a real driven car and a predicted version of it over time. So here we have the mean absolute error of the position, velocity, and the orientation. And what we can see is that by looking at the very first instance of the prediction, so this is how this error evolves over time. So as looking at the first instance, we see the overall prediction accuracy of a specific model. So looking at here, we see that, for instance, model number 4 was the least accurate one within the game, similar to the concept of velocity. On the other hand, if we see the evolution of the curves, so how does it evolve over time, we're capable to understand which is the impact of this error accumulation. From this experiment, so normally what we see, it's a linear evolution of the problem. But the interesting part of this experiment was to understand that despite the model number 4 was the one with the best results obtained within the training environment, when applied to the real game, actually was the least performing one. So this was an important experiment to perform, an evaluation to perform, since it made us understand that not that one of the models that was better suited for the game was actually not the one better performing within the trainings sessions. In step number 9, so now we have a game, we have a predicting module. What we need to do is actually simulate then the disturbances that this module wishes to mitigate. So in fact, what we need to do is create the simulation of the network issues, which is of course the missing and delayed data. This disturbance can be done at two levels. So we have the possibility of doing it at the application level, which of course requires us to have access to the source code. At the same time, though, it gives us greater control. And it means that we are blocking, delaying data and messages within the application itself. The disturbance at the same time can also be done at the network level. So we see the game as a black box, and we just control the data over the network, but without interfering with the game itself. How did we approach this disturbance simulation? We decided to do it at the application level in our car racing game example, creating a discard module. The discard module is simply a software module that discards or holds data and is controlled by two parameters. So the length, which is the time of how much that the disturbance lasts. So it is around so it's the length of the disturbance, sorry. And the interval parameter tells how often in time the disturbance occurs. We define then three different levels of disturbance. So DL1, which has, of course, no disturbance. 2 and 3 have different values and ranges, which are randomly selected throughout the application at runtime. So the final step, now we have all the pieces to perform an actual evaluation, because let's remember that in the end, what we are doing here is not simply ensuring that the data is correctly delivered, but our main and final goal is that of providing a perfect and smooth gaming experience for users. So in the end, our goal is that to ensure that the that the game experienced by players, it's correct, it's smooth, and it's playable. Therefore, a user study should be performed, involving, of course, human players, testing this, gathering data under two main conditions. Of course, playing the game without any network disturbance. So it means using the game with our simulation disturbance module under DL1, so without any type of disturbance. And of course, simulating the disturbance using SPG, of course, active in order to compensate for the disturbances. What should be done? Of course, it is very important to collect qualitative data, which should address three important key points, which is the perception of players of anomalous behaviors. So did the player perceive that other entities in the game controlled by other players had strange movements or did strange, weird things. Of course, the game responsiveness. So the game must be responsive as perceived by the player, and finally an evaluation on the overall gaming experience by comparing the data gathered around these three main scales on the two conditions. We can assess if SPG is therefore contributing positively or negatively to the gaming experience. So what we did in our case, we did a small user study with 12 participants, which the protocol was as follows. So they underwent a training session just to take familiarity with the game controls, the game graphics, and so forth. They then played the game under the three different conditions. For each user, of course, the order was randomized so that we did not have a structured sequence of playing the game without disturbances and then with the disturbance. So this was entirely randomized. At the end of each session, under one single condition, a questionnaire was gathered, collecting data along the three scales that I discussed earlier. On the right here, we can see the results of this questionnaire. The interesting part is that in several cases, the DL1, which means the absence of disturbance, yields results which are similar to especially to the DL2 condition, but in some case, like in the oh, sorry, like in the responsiveness case, it actually even better compared to the DL2 and the DL3 condition. So our experiment, of course, it is shows that we are in a promising direction, so that the general idea of SPG can be therefore explored further because it has some promising approaches. Of course, one of the key issues related with SPG is on the quality of the prediction. In fact, as we can see, the metric and the scale of anomalous behaviors grows as the disturbances grows in the game, meaning that in several instances, players perceive the prediction to not correctly mimic what the player was doing in the absence of data. Therefore, based on this problem and others that we accounted throughout the process, I would like to outline these four future directions that we hope that SPG will be able to pursue. So first and foremost, as I said, the one of the biggest problem was on the prediction side. So either on the computational cost of using an LSTM, as in terms of the quality of the prediction. So therefore, testing with other models, like for example, diffusion models, could be an interesting venue to pursue. Of course, our initial game experience evaluation with human players was limited to 12 players, and it would be really interesting to expand the user base in order to achieve a more comprehensive picture on the qualities and weaknesses of SPG. Another important part, as we have noticed, of course, we have faced this issue of leveraging a synthetic data set, trying to use it with real players, trying to predict real players. Of course, due to this domain shift that we predict real players using a model trained on synthetic data, would be interesting to substitute the synthetic data set with real player data, with data collected from real players. And finally, this is another approach which yields a prediction, but instead of using predictions, the whole system remains the same, but we substitute AI agents instead of using a network model as a predictor to forecast and take over when in the case of missing data. So these are the general direction that we would like SPG to pursue. but before we pursue them, I think we should more. It is important to thank all the people that have contributed throughout the years since the SPG has started. So, of course, Leonardo, which is has been always present and of course a source of great inspiration to pursue to take on the all the challenges and struggles that we have faced during the development of SPG. Marco Mazzaglia, which is also connected and I would say is among the founding fathers of the project and has so conceptualized the project from the very beginning and has uh, given its the kickstart and has let the ship uh, go. Then I would like to thank Davide Cavagnino and Maurizio Lucenteforte from the University of Torino, which have been the counterpart of the helping me and the rest of the team from I come from Politecnico di Torino, so we have been creating this transversal team working together on the project. Well, I would like to thank HP Computing for AI, which is the in the end it's just a network, no network, it's resources that have been given to the University of Torino, which we have leveraged for the training models, for training all the models that we have during the project. And then I would like to thank, really thank all the thesis students coming from either the University of Torino and the Politecnico di Torino, so Antonio Guarino, Giorgio Gamba, and Daniele Spina, which have, I would say, propelled and really made the SPG something concrete and not just an idea and a concept that we were initially that we had in mind. So with this, I thank all the listeners of the that are here today and hope that SPG will continue its path